Alcohols and ethers are both common products of nucleophilic substitution reactions. So let's look at this example where we add a hydroxide to an alkyl halide, and through an SN2, right, we end up with an alcohol. Because remember, these electrons will come in, it'll attack that partially positive carbon, right? And those electrons go on the bromine. Now, I want you to notice that in organic reactions, sometimes we just show the organic product and don't worry about the Br minus over here. And so that's pretty common. And then if we have an alkyl halide with a deprotonated alcohol, the same thing will happen. And it'll go through an SN2 reaction, and we'll end up with an ether. So we have an ether here as a product and an alcohol here as a product. Now, the preparation of an ether in this equation here is called a Williamson ether synthesis. And that's a really common way to synthesize ethers. Now, when we synthesize ethers, right, unsymmetric ethers can generally be synthesized in two different ways, right? So for example, if we were trying to synthesize that ether, okay, and we were going to do this through a Williamson ether synthesis, then what we would do is we would say, okay, I'm trying to synthesize that ether. That means that I need an alkoxide, right, with this oxygen on it to react with an alkyl halide. And so there are basically two ways you can do this. You can put the alkoxide here, right, where we take and we say, okay, hey, look, we're going to split it right through here. And everything here over is going to be that alkoxide ion. And then, right, everything from here over is going to be the alkyl halide. And so we'd say, okay, hey, look, that means the bromine needs to go there. Now, we can do a second reaction where we make this same product. And instead of having the alkoxide and forming the alkoxide ion with just the ether group, we can come here and we can say, all right, hey, look, everything over here is going to be with the alkoxide. And so what that means then is we have, right, O minus like this, and then everything this way is going to be from the alkyl halide. And so we would have a alkyl halide that looks like that. Okay. Now, in each of these, this would give us a secondary alkyl halide. And this would be a primary alkyl halide. Now, in theory, these two syntheses work. In practice, one path is usually preferred. And the path that's usually preferred is this path here. Because that path involves an alkoxide attack on a less hindered alkyl halide. Right? And it's a less sterically hindered. I left out a very important word. It's a less sterically hindered alkyl halide. So look, because this alkyl halide is primary, it doesn't have as much steric hindrance as this alkyl halide does. So this is the preferred path. Now, maybe the burning question in your heart is, Dr. Pierce, we've been using these deprotonated alcohols, these alkoxide ions, quite a bit. How do we make these guys to be in these syntheses? Well, these are referred to a lot of times as alkoxide salts, right? So we have an alkoxide salt, and these can be prepared from alcohols by a Bronsted-Lowry acid-base reaction. So to prepare an alkoxide salt, you start with an alcohol, and then you add sodium hydride. Now, when we come over here and we add sodium hydride, the sodium itself is a spectator ion. So I am going to show this mechanism, and I'm actually going to erase the sodium hydride, and let's put it up here so that you can see the full equation. So when we go through and we do this mechanism, what happens, this is a proton transfer. So this comes over and grabs that proton. The electrons that make up that bond go onto the oxygen, and now you have an alkoxide, and it's an alkoxide salt because the sodium here will act as the counter ion. So, for example, the way you would name this is that sodium ethoxide, right? Just your general alkoxide salt. Then the byproduct of this is really interesting. It's hydrogen gas, right? So this is a gas, and that byproduct just bubbles out of the reaction. So you don't have to go through really any separation methods. Because it bubbles out of the reaction, right, we're continually removing this. And so according to Le Chatelier's principle, right, if this is at equilibrium, it will continue to go towards the products as we move that reactant. So it's a very good preparation of sodium ethoxide by using that sodium hydride. Now, let's think about, how do we synthesize an epoxide? Okay, well, one of the ways that we can do this is to use a halohydrin, right? So a halohydrin is just a compound that contains both a hydroxy group and a halogen atom on adjacent carbons. So, for example, a halohydrin look like that with an OH here. Now I'm drawing that OH out because we're going to take it through a base, take it through a reaction using a base. So in halohydrins, we have a intermolecular version of the Williamson ether synthesis, and that can form epoxides. And so what happens here is we have a generic base, right? And that generic base will come here and it will steal a proton. So it goes through proton transfer, and those electrons will go there. Now, when it undergoes that proton transfer, now I always like to draw the things that don't react first. It's just my preference. We have this oxygen, and it has a negative charge on it. Now, this oxygen with its negative charge can act as a nucleophile. So that means it's going to come down and attack the partially positive carbon that's attached to this halogen, because the halogen is withdrawing electron density. That makes this partially positive. This acts as a nucleophile. So we go through an SN2 reaction where these guys, these electrons come down, they attack that carbon, and those electrons go on to that halogen. And so when we do that, we now form our epoxide ring. Okay, so we've learned so far how to prepare alcohols and epoxides. And so now maybe what you're curious about is what type of reactions can alcohols and ethers and epoxides undergo, right? Well, let's talk about this a little bit. Unlike alkyl halides, right, where in a substitution reaction, the halogen is a really great leaving group, this OH is a pretty poor leaving group, okay? And so this reaction tends not to go. So what we do as scientists is we convert the OH into a better leaving group. And we do this by treating it with a strong acid. So we treat the alcohol with a strong acid. So when we do this, what happens here is we have our friendly alcohol, we react it with a strong acid, undergoes a proton transfer reaction where those electrons grab that proton, those electrons go on the chlorine, right? And now we have OH2 with a positive charge, and that is a weak base and a great leaving group, okay? So this is a way that we can convert an alcohol into a better leaving group. And this makes it possible to perform substitution and elimination reactions on alcohols. And we are going to talk about elimination reactions in just a second in this screencast. So, like alcohols, ethers do not contain good leaving groups. Okay, so this ROR, which is our ether group, that's just a poor leaving group. So what that means is ethers undergo fewer useful reactions compared to alcohols. And that's okay, because that means we tend to use them as solvents. Because they will not go through reactions that alcohols will necessarily. And so what that means is that they will be a great solvent that doesn't react or have any side products that we have to worry about. So now what about epoxides, right? Well, epoxides has the same type of leaving group as ethers, right? When we think about an epoxide, that's what an epoxide looks like, but an epoxide does readily react with a nucleophile like this, right? And what that does is it will open up the ring like this. Now, this strained ring is quite reactive, more reactive than the ethers. And so by going through this reaction, it will open up and it will relieve angle strain. Okay. And so that's why epoxides are more reactive than the ethers. Now, alcohols can undergo a dehydration reaction to form alkenes. And when we talk about this, right, one of the types of reactions that alcohols can undergo is dehydration. And dehydration is really similar to dehalogenation. And so let's look at this molecule here. Okay, and so this is another example of a beta elimination reaction where the OH and the hydrogen are removed from the alpha and beta carbons. And so when this occurs, when those are removed, we get a new alkene at the alpha and beta carbons. So we get a new pi bond. Then we also produce water. And so the way I think about this is like if you're really dehydrated, you've lost a lot of water. This is a dehydration reaction and we lose water with this. And so that's how I remember kind of what a dehydration reaction is. Now, dehydration reactions generally require really strong acids. So right? These are typically carried out using sulfuric acid, right? Phosphorus oxychloride is another example of a really strong acid that's used in the presence of an amine. And then we can also use the P-sulfonic, toluene sulfonic acid shown here. It is abbreviated as TSOH. And that is also a really strong acid that can be used. And so, for example, if you were to look at a reaction like this, and here's where reactions sometimes get tricky, is it's just going to show you the OH, right? And then it'll say, okay, hey, look, here's the P-toluene sulfonic acid, right, which is an abbreviation, and you have to predict the products. They're expecting you to know, hey, look, there's going to be a hydrogen there on the beta carbon, but they're not going to draw it in for you. So you have to be able to recognize that and then know that that's going to go through a dehydration reaction and form a double bond with the alpha and beta hydrogen. Now, there are reactivity differences with these alcohol groups. And so I want us to look at that really quickly. So the more substituted alcohols here dehydrate more easily. And so what that means is they are the most reactive, with secondary alcohols following and then primary alcohols following. Well, then, of course, the question here is, what about Zatsev's rule? Now, before we get into Zatsev's rule, I just want to remind you the reason we see this is because of carbocation stability. Right? Particularly for the SN1 and E1, right? So just kind of be aware of that. That's why we're seeing that, because we're going to see a carbocation intermediate with E1 and SN1. So don't forget that there's a carbocation intermediate there. So now back to Zatsev's rule. When an alcohol has two, right, or three different beta carbons, so these beta carbons here are chemically equivalent. This one is different. Dehydration is generally regioselective, and it follows Zatsev's rule. So that means the more substituted product here is the major product, where the minor product is the less substituted. In reality, you get a mixture of these. You just get more of this because it's more stable. Now, let's look at these mechanisms. Secondary and tertiary alcohols react by E1. Right? Whereas primary alcohols react by E2 mechanisms. So I want us to look at that E1 mechanism with an example using an alcohol. So let's say we have an alcohol here, and we need to turn the OH into a really good leaving group. And so we are going to add sulfuric acid. Now I'm going to draw sulfuric acid like this because the first step here is a proton transfer. So what happens then is that these electrons come and they grab the proton from that sulfuric acid. These electrons go on the oxygen. When they do that, this alcohol is protonated, and that makes a really great leaving group. So now what's going to happen is this is going to go through heterolysis, where that alcohol just happily breaks off to form water. I'm going to write that step down, and that's a proton transfer. And you'll see these steps repeat, so it's nice to see the same patterns over again. And so now, when we go through heterolysis, we have a friendly carbocation here. And we have to remember and draw in that there is a proton there. Okay? So you have to draw that in. Now, the base comes back, and you're going to see this one of two ways. You're either going to see, right, the OSO3H with a negative charge here. Sometimes you'll see it as HSO4 minus. Sometimes you'll just see it as a base, right? So you kind of have to recognize both things. I like showing it this way because I like to draw my electrons in, just honestly. So I have my electrons here. They are going to come, they're going to steal the proton on the beta carbon, and then these electrons are going to come right here and form a double bond. And so this, through the elimination reaction, gives us the double bond here. Now, E1 dehydration of secondary and tertiary alcohols gives very clean elimination products without any byproducts from SN1 reactions. So you end up with no byproducts from SN1 reactions, right? And so clean elimination takes place because the reaction mixture contains no good nucleophile to react with the intermediate carbocation. So you don't have any competing SN1 reactions. There are no good nucleophiles here. This makes the E1 dehydration of alcohols much more synthetically useful than the E1 dehydrohalogenation of alkyl halides. So now let's look at an E2 mechanism. When we come here to do this E2 dehydration, right, we're going to see a lot of similarities, particularly here at this first step. This first step starts with a proton transfer, where these electrons come and they grab that proton, and those electrons go on the oxygen. When that happens, we now have that protonated alcohol. Now, when we look at this, right, you have to identify that this is the alpha carbon, and that makes that the beta carbon, and then you have to draw in that proton. Okay, so don't forget to do that. Then we have the sulfuric acid that comes in here, where we have SO3H, and I always like to draw that oxygen here. with its negative charge, and it's going to steal that proton. When it steals that proton, these electrons jump down here to form a double bond, and now that protonated alcohol makes a really good leaving group of water. And so that means for us, right, we formed our new pi bond here. We have water as a good leaving group, and then we also regenerate our sulfuric acid we started with, and so that, of course, acts as a catalyst. Now, I want to point something out here. Entropy favors product formation in dehydration, right? So entropy favors the product formation in dehydration, since you have one molecule of reactant right here forms two molecules of the product. This just gets regenerated, right? But we have one molecule here forming two molecules here. It's favored by entropy. Now, enthalpy here favors the reactants, since you have two sigma bonds are broken in the reactant are stronger than the sigma and pi bonds formed in the product. And so that's, it's always a really interesting balance when we start to talk about entropy and enthalpy here. Now, so let me make a note about enthalpy, because I don't want to forget. I want you to have that. So enthalpy favors the reactants because two sigma bonds are broken in the reactants, and those are stronger than the sigma and pi bonds formed in the products. And so product formation here can be favored using Le Chatelier's principle. Right? So what happens here is that we can remove the product from one of the products here as the reaction is continuing. So we can use distillation to remove the alkene, right? Which usually has a lower boiling point than the starting alcohol. And so it's removed by distillation. And so it drives the reaction this way. And that's how we can get over the enthalpy issue that we have here. So it's a really kind of smart way to do this. Now we have one other kind of interesting thing that happens when we look at elimination reactions. So we have something unusual here. So if we look at this reactant, this is 3,3-dimethylbutane-2-ol, we would expect when this goes through an elimination reaction to form a double bond here. And what we find instead is neither product does that. And so that's really weird. And so as chemists, that's generally, when weird things happen, that's generally pretty exciting, because that means the mechanism isn't what we would necessarily expect. And so the question becomes, why did this happen? Well, often when carbocations are intermediates, a less stable carbocation will be converted into a more stable carbocation. And this occurs by a shift of a hydrogen or an alkyl group. Now, this is called a rearrangement. And we're going to look at that mechanism we're going to look at this mechanism in 2 slides so we can see how these 2 products form. But first thing is, how do we know that a rearrangement occurred? Well, as I pointed out already, right, we end up with a double bond in an unexpected location. And that's the biggest clue that a rearrangement has occurred. Now, let's look at the different types of rearrangements. So in one type of rearrangement, what you can have is a hydride shift. And so when we look at this hydride is shifting just over 1 carbon. And when the hydride shifts, it takes its electrons with it. And now we have another carbocation here in a different place. I want to point out something. This goes from a secondary carbocation to a tertiary carbocation. Tertiary carbocations are more stable. This is why it occurs. Now, when we talk about this, right, you can see a hydride shift. You can also see a 1,2 alkyl shift. And in a 1,2 alkyl shift, for example, let's say you have this guy, right? So you have that guy, okay? And what can happen, right, is that the alkyl group can also shift over right to there. When that alkyl group shifts over, again, we went from a secondary carbocation here to a tertiary carbocation here. So this is a 1,2 alkyl shift when an R group moves. This is a 1,2 hydride shift when a hydride moves. So when we talk about this, and I've already mentioned this, but why does this happen? Well, to convert a less stable carbocation into a more stable carbocation. So it does this to increase the stability of the carbocation. Anytime you form a carbocation, you must evaluate whether you're going to have a shift, okay? You will have shifts from a secondary carbocation to tertiary, a primary carbocation to a secondary, a primary carbocation to a tertiary. If you have a tertiary carbocation out of the gate, you will not have a shift, okay? Because that's already as stable as it gets. So that's something to kind of be aware of. Now, unless there is an option for resonance, and we're going to talk about that later. So I don't want to give you an absolute, and then us get to an exception down the road. If there's an option for some resonance stability, then sometimes, very rarely, you'll see a shift. But in what we're going to see with the tertiary carbocations here, you're not going to see a shift. So I want us to go back and look at the mechanism and of what we saw with the dehydration of 3,3-dimethylbutane-2-ol. So I'm going to start with my happy 3,3-dimethylbutane-2-ol here. And it's going to go through a dehydration reaction, which means it's going to react with a strong base. So I'm going to use sulfuric acid. And so remember, you have to draw your electrons in. So these electrons are going to come here. They're going to grab a proton. These electrons are going to jump right there onto the oxygen. Now, when they do that, right, we form this really great leaving group. And so this undergoes heterolysis, where this bond breaks and those electrons jump down there onto the oxygen. So we have a proton transfer. We have heterolysis, right, of that E1 reaction. Then we end up with a carbocation. And so this is the carbocation that we end up with, right? And that is a secondary carbocation. Now, at this stage, you always need to stop and look for a rearrangement, always. It's one of the trickiest things in organic chemistry, in my opinion, right? Is we have to stop here and say, look, can anything shift to make this more stable? We have to remember there are hydrogens here, right? So could one of those shift here and make that more stable? Well, no, because if it shifts here, it gives us a primary. So could something over here shift? There's no hydrogens, but there sure as heck is an alkyl group there. So what happens then is we have to recognize and say, hey, look, this alkyl group, we're going to see a shift right there. And so we see a 1,2 alkyl shift. When we see that 1,2 alkyl shift, now we have a tertiary carbocation. Okay. Now that tertiary carbocation gives us two different hydrogens. So my suggestion at this stage is to draw in your hydrogens here. We have, when we look at this, right, hydrogens here, here, and here. There are three of them. And then we also have hydrogens, or a hydrogen, right here, okay, because there's no charge. That means that carbon needs 4 bonds. So when we talk about this carbon being the alpha carbon, now on the beta here and here, we can remove a proton from this beta carbon or this beta carbon, okay? So when that occurs, and I'm going to show both of them, I'm just going to rewrite it and show both of them down here. So for example, okay, let's say we are going to remove this proton first. So okay, so this molecule comes in, that conjugate base of the sulfuric acid, it's going to steal the proton. When it steals the proton, those electrons go down and make a double bond. All right, and so there's one of our products, and that's where we found that beta hydrogen. Now, this can also react a different way, where it can react with one of the protons on the CH3 that's shown right there. And so now it comes in, it's going to grab that guy, and those electrons are going to go there. And now we have that product. Now, I always stop here and double check. When I double check, I count my carbons. 1, 2, 3, 4, 1, 2, 3, 4, and then 5, 6, 5, 6. So whenever I'm doing mechanisms, I'm always making sure my structure that I draw here, I count the carbons as a double check, And then I also double check that that double bond is going where the mechanism says it should be. So the double bond's here, and that double bond is here as well. Look, these are sneaky. In my opinion, this is the sneakiest thing that we do in organic chemistry, are these carbocation rearrangements. No matter what mechanism you're doing, if you form a carbocation, you must check for a carbocation rearrangement. Now, carbocation rearrangements aren't inherently bad, right? Maybe we want to synthesize this product, right? This would be a really savvy way to do it. But they are tricky in such a way that we have to kind of always be on guard with them. We are going to practice this more in class. If you have any questions, please feel free to stop by my office or reach out via email.